So good afternoon to all the participants. I welcome all of you to the last day of our online faculty development program on cloud and fog computing platform for IoT application organized by E&I City Academy and Department of Computer Science Engineering, NIT Warangal. So today we have two sessions. In the first session, we'll see one of the latest computing paradigm that is called as osmotic computing. So it is a very emerging paradigm between cloud and edge and IoT. And the second session, we will discuss building of smart IoT system, some of the challenges and their possible solutions. And it will be taken by Professor Chittaranjan Bhuttar from Department of Computer Science and Information Systems, BITS Pilani, Hyderabad campus. So let us start the first session, in which I'll tell you about a very recent computing paradigm that is called as osmotic computing. So you can find very less article in the field of osmotic computing, because this computing was started or was proposed in the year of 2016. You can say around 7 to 8 years back. So this computing paradigm bridges the gap between cloud and edge computing, or you can say cloud and fog computing. On the other hand, it is also bridging the gap between edge and IoT, or you can say fog and IoT. So here I am using the term fog and edge alternative, but actually there is a difference between the fog computing as well as edge computing, that I'll tell you in this particular session. So what are the topics that we are going to discuss in this session? I'll tell you the roadmap of a computing paradigm, because we know before cloud computing, there are several other computing paradigms are there. Like we discussed in the very first lecture related to parallel and distributed computing. We have discussed about cluster computing. Then we discussed about grid computing. We have seen also utility computing before discussing the concept of cloud computing. So we'll see the roadmap of uh, computing paradigms, starting from the first computer to, you can say, osmotic computing. Then we'll discuss about three different architecture. Earlier architecture, if you remember, we have mainframe systems, which is a very bulkier system, very heavyweight and very large system. So such systems are called as the monolithic system. Then after monolithic system, we have service-oriented architecture. So in cloud, basically, the background of cloud is service-oriented architecture. And nowadays, microservice is very popular. So we'll see the difference between the monolithic architecture, then service-oriented architecture, then the latest concept, that is microservices. So as there are very less article available in osmotic computing, so if you go to any database like IEEE, ACM, Elsevier, Stringer, where you are getting research paper, so if you search about osmotic computing, you will get very less number of articles. So there is a huge scope for us to work in the field of osmotic computing. So what we did when we we started our research work in the year of 2018 and 19 in the field of osmotic computing, that it is very challenging at that time. Again, very few articles are there, hardly 20 and 30 articles are there. So we have done a systematic review process. So whenever a new computing paradigm is coined, then people are very much interested to write a review paper. So we started the process of systematic review process. So there is a difference between review article and systematic review article. So systematic review article is having certain guidelines. So you have to follow certain procedures if you want to conduct systematic review process review of a particular area. So how to carry out that systematic review? I'll tell you. It is also covered as a part of research methodology if you have taken during your MTech or PhD time. Then we framed some of the research questions related to osmotic computing. So I'll show you what are the research questions we have framed and what are the search strategies we have applied to extract the paper from various databases, and what are our selection criteria and what are the exclusion criteria. So what are the criteria to select a particular paper for review, include in your review process, and what are the criteria to exclude a paper from the review process? That also we have carried out. Apart from that, we have also taken some of the quality assessment questions. So these questions will help you to get a value. Let's say if you are taking 5 quality assessment questions, then you will get let's say value of 5 by considering each question is having one maximum mark of 1. And you can say if a particular research article satisfy the requirement, then we give value 1. If a research article partially satisfy, we give the value 0.5. If an article is not satisfactory, we are giving the value as 0. So we have made some quality assessment questions to find a particular value for each and every research articles or contribution article which we found in this particular field. But number of research articles are very, very few, and the number of review articles are again quite few, and systematic review is very, very few. And I can say this is the first article which was published in ACM transaction on IoT by our research group. Then we'll see some of the relevant studies related to osmotic computing. Especially we'll see in what are the areas people have concentrated, and they found that osmotic computing is a appropriate paradigm in that particular applications. For example, you may ask, if I want to go for healthcare application, can we apply osmotic computing? Or if you want to go for the smart city application, where IoT is there, fog is there, cloud is there, can I go for osmotic computing? So that questions we have also addressed in this particular paper. Then I'll show you the osmotic computing ecosystem so that you will know what are the different layers available in the osmotic computing, how the transition made from one layer to another layer. It is also important to compare cloud with fog, with edge, with osmotic computing. Okay. Normally, we consider IoT is also a part of edge computing. If we want to show IoT edge is a single layer. So we have compared all these 4 computing paradigms with respect to certain characteristics to decide that in which case cloud is better, in which case edge is better, which case fog is better, in which case you can go for osmotic computing. And we'll see certain applications of the osmotic computing, like I mentioned, healthcare. We'll check whether we can use osmotic computing in healthcare or smart city application, or in blockchain. Can we apply so osmotic computing paradigm and so on. Then I'll tell you a very simple task mapping algorithm, which is having 2 different steps. One is task level, another is called as processing level. So in the task level, we categorize the task into different types, right? Like I can, in general, I can say a task can be categorized into small task, medium task, or large task. So we have made some categorization of the task. Similarly, we have made the categorization of different processes. Like there are high-end processes are there, there are low-end processes are there. So we can do a categorization. And this task mapping algorithm, what actually it does, it maps the task with the resources, that is the processing level elements. So that algorithm will discuss, followed by the conclusion and references. So let us start with the introduction. So all of us know the father of computer is Charles Babbage. So he has shown a prototype. Not, we can say, even if that is not a prototype, it is a simple version, you can say, of a computer system. So 1822, first computer, he suggested that what are the different components of a computer system. Okay. Later it is formalized by John von Neumann architecture after a long time. But a computing machine it was suggested by Charles Babbage long back 1822. And you can see after almost 100 years, we have mainframe computer. So hardly one country is having a handful number of mainframe computer on those days. And mainframe computers are generally made up by vacuum tube, and they are very heavy in size. The size of mainframe computer is very it also occupy a large amount of space, and also the size is also very heavy. So it is not possible for mainframe computer to move from one place to another place. So mainframe computer normally takes the task in the form of a batch. So if you want to execute your program, then if today you will submit, maybe tomorrow or day after tomorrow, you will get the output. Okay, so it is not interactive, you can say, right? Because those days we have very less amount of computation. Also, we have less number of computing devices to execute our program. But in 1945, after 15 years of the mainframe computer, so we have electronic numerical integrator and computer, which we call as ENIAC. This computer was suggested, and this computer normally, up to this computer, everything is represented in the form of a decimal number system. For example, if I ask you how a computer stores our data, then all of you will say it is storing the data in the form of 0 and 1, right? But ENIAC computer, up to ENIAC computer, all devices represents the data in a decimal number system, not in binary number system. But EDVAC, that is called as electronic discrete variable automatic computer. So EDVAC is the first computer system where the binary number system had been implemented, right? So EDVAC is obviously an improvement over ENIAC, but most of the functionality that is available in ENIAC, that is also available in EDVAC with some additional features. But till EDVAC, nobody thought about the parallel computing paradigm. Today we say about IoT, fog, cloud. These all are parallel computing paradigm. They are not sequential paradigm. That's why these are called as the family members of parallel distributed computing or parallel distributed systems. So in 1950, people have thought of parallel computing because our computers are having multiple processors. So if a computer system is having multiple processors, like we have symmetric multiprocessor, we call it, that is SMP. So if you have multiprocessors and if you are doing your work sequentially, then other computer, other processor, what you have in your system, it is completely idle. So we are not using that particular system. So parallel computing enables us to write the code in such a manner that both computers will get some kind of processing, or some kind of data to process in their processor. So no computer is going to be idle. At later point of time, people have thought about large-scale computer architecture. So in which they thought that why not we combine certain machines or a group of machines to achieve the power of a large-scale computer. So Soon after that, we have the concept of cluster computing, which we discussed earlier. So in which all the nodes are having homogeneous in nature, their architecture, their operating system, and their properties are more or less same. So they can be clubbed into a group, and one of the node can be considered as the cluster manager, which is going to coordinate all other nodes. So that is the concept of cluster computer. But mostly the cluster computing is, you can say, these computing paradigms are implemented in a particular lab. So we are not going beyond the particular lab, right? We is restricted to a particular organization, restricted to a particular building to form a particular cluster. So later people come up with the concept of distributed computing. In distributed computing, all the computers are present in different locations. They are not in the same location. So it increases the reliability because probability of failure is very less. Even if there is a failure, it is not going to impact much. And they are located in different locations, different maybe different countries, different continents, and they are doing the parallel process. So the concept of distributed computing was started from the year of 1970. So till 1970, nobody has thought of going for, we can say, personal computer. So the first non-kit personal computer is Miracle N, was prepared in 1973, but Altair is called as the first personal computer. This is the first personal computer initiative, but later, uh, actually, the personal computer uh, which was set up is called as Altair. So this is the first personal computer. Nowadays, we all of us are using personal computer PCs, maybe a laptop or a desktop or a tablet or a personal digital assistant or maybe anything. So all are personal computers. But it was started in the year of 1974. Soon after that, 1980, we have client server computing. Client is less powerful, server is more powerful. Client is making a request to the server, and server provides the resources to the client. Then after that, due to the invention of, you can say, internet was invented by ARPANET, all of us know. So ARPANET discovered, invented the internet. So through internet, the devices can be connected. So these distributed computing paradigms are enabled through internet. Like, whenever you are searching in something in Google or any search engine, so you know that the server is not close to us. The server may be somewhere else, but we are able to connect to a particular server through the internet. So internet-based distributed computing started in the year of 1988. 1990, Ian Foster, who is the father of grid computing. Okay, so he told the concept of grid computing in a international conference, which was accepted by the community, and grid computing was started in 1990, where nodes are considered as heterogeneous. Nodes are not homogeneous; they are completely heterogeneous. Their system configurations are different. Like if I ask you your system configuration, and if I tell my configuration, so it may not match, right? Your system may be a high-end system, my system may be a low-end system. You may use different operating system. I am using different operating system. So still we can combine the machines, and we can save the resource. We can aggregate the resource. So grid computing enables it. So it was started in 1990. And the concept of edge computing is also was also started in 1990. Although the concept of edge computing is nowadays very popular, but it was quite old. The concept of utility computing started from 1998, where the concept of service is coined. So based upon our usage, the service is going to be charged. If you are using more, then you have to pay more. If you are using less, then you have to pay less. Then cloud computing is also popular using the virtualization technique, through virtualization technique on top of a physical machines, by the help of a hypervisor, we can create multiple virtual machines, right? VM1, VM2, VM3. So this is a virtualization technique. Hypervisor enable us to make a abstraction, or a hypervisor is providing just like a middleware to create multiple virtual machines by taking the resources of a physical machine. So the concept of virtualization is also not new. It was started from the year of 1990. And cloud is also based on a Web 2.0 technology. Current version of uh, Web is Web 3.0, but Web 2.0 is also one of the backbone of cloud computing. Then people have come up with peer-to-peer computing. In peer-to-peer computing, we know every peer is independent, right? They have their own memory, and they can share the resources with other peers to compute some work. So it is a part of distributed computing, right? So peer-to-peer computing was started from 1999, and in 2006, people have started the concept of cloud computing. Okay, and 2009, there is a concept called orientation. So it is also based on the service-oriented architecture. So all the services are not like earlier systems; they are tightly coupled system, right? Everything is done by one particular unit. So later point of time, these modules are decomposed. They are divided into small parts. So they treat just like in service, right? The service orientation concept was started in 2009, and in 2012, Cisco started the concept of fog computing. So in which they says that the resources becomes available near to the user. Cloud is very far to the user, so we can provide the resources which is close to the user, right? So they started the Cisco started the concept of fog computing, and it was very popular because it is distributed hierarchical structure, and fog also provide faster solutions in comparison to the cloud or smaller computation, right? So fog computing was widely accepted by the community. But in 2016, the latest computing paradigms started, that is called as osmotic computing. In osmotic computing, basically, we are integrating multiple technology into a single platform. That's why osmotic computing is not fully mature now. It is in immature state. So there are a lot of areas which are open for research. So maybe after a couple of years, osmotic computing may be a popular paradigm, just like cloud and fog and IoT, or you can say blockchain, or you can say artificial intelligence or machine learning. Now coming to the definition of osmotic computing. So osmotic computing is just like a other computing paradigms which we have already seen. Some of the related paradigms we have already seen, like IoT. Then we have seen edge, fog, and cloud. So it is based on these four different technologies, you can say. One is IoT, another is edge, another is fog, another is cloud. So what kind of solution it is going to provide? So osmotic computing is providing you the solutions for handling bulk of latency sensitive data generated by the digital devices. So you know, in our day-to-day life, we are using various digital devices. Our smartwatch can be considered as a digital device. Smartphone can be considered as a digital device. Tablet, others, these are called as our digital devices. So these digital devices are generating the data. If the data is a latency sensitive data, latency means we can say it is a delay, right? If delay is more important for these devices, then we call that is a latency sensitive data. Suppose you want to do a computation urgently. So if there is any delay, it leads to a large failure. Then we can call that as a latency sensitive data. So osmotic computing provides solutions to latency sensitive data generated by any device. So if it is not latency sensitive, you can go for any computing paradigms, like cloud is best for if it is not latency sensitive. But if it is a latency sensitive one, then if its delay is more important, right? Delay is more important, then definitely you can go for osmotic computing, because osmotic computing is going to provide you a solution. So what you can do in osmotic computing, you can deploy the microservices. Suppose there is a microservice you want to deploy, so osmotic computing can help you. If you want to migrate your service from one platform to another platform, osmotic computing can help you. If you want to optimize your application, there also osmotic computing can help. So more or less, it is a microservice based uh, system, right? So if you want to migrate or deploy or optimize or providing better solution, in that case, you can go for osmotic computing. So obviously, it promotes digital transformations, because in digital transformations. So today we have, let's say, we put our application in a particular server. Tomorrow we have seen there is some scalability issue. Then we can migrate from one system to another system. Migration becomes one of the important part in digital transformation. Like traditionally, you are using some system, but in the modern architecture, you want to move to another system. So there also digital transformation is required. So all these things you can get by the help of osmotic computing paradigms. So some of the popular application in osmotic computing is our transportation. Like if you are traveling in a particular national highway, if there is any accident happen, okay, let's say next to from your current location to, let's say, another 2 kilometers, so there is an accident happen and you are close to that accident location. So you will get some signal that no, there is an accident in this location. So you can change your route to, let's say, another route. So that is the objective of smart transportation. In smart transportation, it is also navigating you to your destination by showing the best route at any particular time, right? Similarly, if you go for smart city applications, we are talking about the smart transportation. We talk about the smart building. We say about the smart traffic system. Or this is also, we are generating various latency sensitive data. So if there is any delay, it is going to impact. So within a particular time frame, you have to provide the solution. So there also you can use osmotic computing. In education also, you can go for osmotic computing. Because there are many data which are very confidential, or they are very sensitive data. So in that case also you can use osmotic computing. Similarly, if you go for healthcare also now patients are equipped with, patients are generally when they admit, so in the hospital bed, they are they are placing different kind of sensors. So these sensors are also taking readings. So if the reading is abnormal, if it is emitting a particular range, then the healthcare professionals need to be informed immediately. So that is also a latency sensitive data. There also we can use our osmotic computing. Or you go for industry 5.0 or 4.0 earlier. So where we focus on cyber physical system, we focus on we can say artificial intelligence, machine learning, blockchain, cloud computing. So all these data, if it is latency oriented data, then we can use osmotic computing. So if you want to start your research, or if you want to assign a research topic to your students, then I mentioned a paper in the footnote. The paper title is Osmotic Computing, a new paradigm for edge cloud integration. This is the first research article which was published in the year of 2016 in the Journal of IEEE Cloud Computing. So you can refer this particular article, which gives a brief idea related to the osmotic computing. Now, if you take what is the difference between monolithic architecture and microservice based architecture, so you can see with the help of this particular example. So earlier, monolithic architecture means, you can, I'll show you this particular diagram so that you can understand. Monolithic means it is a completely single unit. Okay, there is whole system is considered as a single unit, right? So if you want to provide an solutions, so you treat that entire thing is a single solution. So solution is built as a one large system. with a single code base. So what happens if there is some minor problem happen in your system, then the whole system is idle or it is not doing any work. So in order to avoid that we used service-oriented architecture. In service-oriented architecture, we decompose the single unit into various sub-units. Okay, the single unit is again breakdown into number of units. So service modules interact with each other to carry out a specific business objective. For example, let's say one particular unit may be target towards uh, ordering a particular service. Another may be uh, a service may be packaging unit. Another service may be shipping unit. Another service may be notification unit, and so on. So earlier, everything we clubbed into a single unit, but now we decomposed into multiple units. Okay, that is called as coarse grain. Coarse grain means, for example, it is an informal example. I can say, coarse grain means if I ask you what is your home address, and you mention home address is, let's say, street number one, flat number this one, second floor. If you write in a single field, okay, if address is asking, I'm asking address to you, and there is a field. In that field, you are mentioning everything, including district name, state name, country name, and all other things. So that can be considered as a coarse grain. So it is not in a minute level, detail, not in a detailed level. But on the other hand, I can make address like this. I will mention, you write the address, in which I will ask you, you write the street number. For street number, I have a field. For flat number, let's say I have another field. Or floor number, I have another field. Okay. Or I am writing next one, street name. That may be considered as a another field, right? Then let's say district name can be considered as a field. State name can be considered as another field. And PIN number can be considered as another field. So if you see in the first one, where we are writing everything into a single one. Okay, so that is an example of a coarse grain. So everything is represented in the form of a single field. Or explicitly you are asking, write the pin in another field. Okay, so you will write all the things except the pin here. Then you will write pin. So that is called as a coarse grained structure. But fine grained structure, we are going for the same thing but in a detailed way. So what is the advantages? The advantages is that, suppose I'll ask you how many people belongs to a particular district. You can easily extract how many people are staying in the street number X. That you can easily found. But in the case of coarse grain, it is difficult to identify. That's why service-oriented architecture was started. But people are again, they are not happy, because although suppose packaging unit is not working, if packaging unit is not working, it is not going to compare ordering unit, notification unit, and shipping unit, right? Although there is an interaction between these modules, but they are not fully dependent on each other. Okay, if they are dependent, the task is going to be wait, right? But if it is not dependent, then every module can work. So it is not just like a monolithic system where there is a single code base, rather than we divide into multiple code base. But when we go for the concept of microservices, the microservice is based upon the microservice architecture. We can say it is an architectural style that structures an application as a collection of services. For example, I can say this is an application where we have several services. You can say 1, 2, 3, 4, like that. There are 16 different services. Okay, and these services are independently deployable, and it is loosely coupled. Okay, loosely coupled is also, you can see SOA is also a loosely coupled, but not like I can say microservices. Or I can say monolithic is tightly coupled. It is quite more tightly coupled than service-oriented architecture. Again, I can say SOA is more tightly coupled than microservices. Either you can categorize it in loose coupled and tightly coupled, but it is not strictly tightly coupled. So it is completely a loosely coupled system. So both, you can say SOA and microservices, they are loosely coupled system in overall, and monolithic architecture is a tightly coupled system. Okay. So all the services are independently deployable. They are not dependent on each other in the microservices. That's why microservices are called as lightweight services, but monolithic is heavyweight services. And SOA is in between the monolithic and microservice architecture. So in order to discuss this thing in more detailed way, you can see this slide. Like all of us are doing shopping through e-commerce sites, right? Like Flipkart, Amazon, or any other sites. So they have implemented the microservices architecture. For example, if a user has selected a particular item and added that item into the cart and then place a particular order by paying the amount. So the first step the user is doing is placing a particular order. So there is a order service unit, right? It is a service. So order service unit receives the order from a particular user, and once order is received by this particular unit, the order is sent to a PubSub model. So PubSub model is called as publisher and subscriber model. Okay, publisher and subscriber model. So YouTube, which we are using in our day-to-day life, it is an example of a PubSub model. Because you know, in YouTube, there are several types of channels, right? So there are different channels are there, right? You may have subscribed to some of the channels based upon your interest. Like there is different videos related to different topics. There are videos related to music. Okay, so there are different type of channels are there. So if you have a subscribed to a particular channel, suppose I have subscribed to one channel. Let's say if you go to YouTube, I have a channel with my name, right? Suppose I have a channel like this, right? If you go to this particular channel and press subscribe button, okay, subscribe button. So you have subscribed to this particular channel. So whenever I'll post a new video into my channel, okay, whenever I'll post a new video into my channel, like this FDP, I have pasted all the videos into my channel. So if you are subscribed to my particular channel, whatever the new videos I am going to post, so that you will get a notification. Okay. So whenever you are getting a new thing, then that you will be notified because you have subscribed to that particular channel. So I am the publisher and you are the subscriber. So whenever a publisher gives a new notification or add a new type of thing into the channel, so all subscribers are notified. The subscriber will get the details about that particular thing. Okay? So that is an example of a PubSub model. So here you can see why we are using a PubSub model. PubSub model is not only used in YouTube, but it is used in various domain. For example, once order is received from a particular user, the PubSub model is a unit which is going to inform to many different services, or is going to invoke many different services or inform different units about this particular order. For example, it has to inform the packaging services that the order is received and the order details is this much and you have to pack this particular order. Okay. Another in this PubSub model also can inform to the shipping service that one order is received and I have informed to the packaging unit that they will pack it on this particular date and you have to ship to a particular location. Similarly, PubSub model is also going to inform to the notification unit that periodically you have to send the notification to the user. Like whenever we are purchasing a particular product, we are getting message when the order is successfully placed. When the order is shipped, we are getting order. When the order is near to our nearest center, we are getting an order. So that is the responsibility of PubSub model. Okay. So it is informing to the packaging unit, that is order event received, then order packaged event when the order is let's say packed. Okay, then packaging unit has to inform to the PubSub model. So PubSub model will inform to the shipping service that order is packed and it is ready to dispatch, right? Or it is ready to ship. Then once it is shipped, shipping unit has to again inform to the PubSub model. right? That is the order is successfully shipped. Then whatever we are doing with respect to this one, everything will be notified the notification services. The notification service will be periodically inform the user and different units that this order is successfully placed or this order is successfully dispatched. This order is received by the customer. Everything will be done by the POPSub model. So behind these particular, these are treated as different type of services. Just as I show you, these are the different type of services in fine-grained architecture or coarse-grained architecture. So here also these are treated as a services. So these services are independent services. Okay, but there is a workflow, right? Like PubSub model has to informs to others, and it has to also get the notification from others, right? Although these services are working as a single unit, if you take in overall way, but inside that they are independent units, right? For example, periodically a particular unit is not working, then those orders are placed in the pipeline. They will process. They will not wait, right? But when if there is a dependency between two different units, so definitely they have to wait. There is no other option, right? So you can see Cloud SQL, which is a very popular database point of view. SQL, we know that is structured query language. We write different kind of queries onto a particular database, so that database can help us to extract the information, right? So microservices enable us to break down a very large application. This is a very large application into smaller independent services. Like this example, specifically, as I said, order is considered as a service, packaging unit is considered as a service, shipping is a service, and notification is another service. So like that, for each and every type of application, if it is decomposable, note that all applications are not decomposable. It is not possible to decompose all type of applications. Like the application is decomposable if there is some independent unit, right? If they are not independent, it is not possible to decompose the application, right? Now, if you go for cloud computing from, as I said that osmotic computing is a related paradigm of IoT, AS, fog, and cloud. So we should know the cloud-based taxonomy. So what are the cloud-based taxonomy? So overall, the cloud-based taxonomy is divided into two parts. One is called as short-running task, another is called as long-running task. Because when the task is small, it is possible to handle that task in IoT layer or edge layer or fog layer. When the task is very large or long-running task, so you have to go to the cloud. Right? Again, if you go for the short-running task can be divided into HPC task. HPC, we know that is high performance computing, in which we have CPU plus GPU based system, right? So GPU based system help us to execute in a very faster way. Okay. So, or it may be a data intensive applications. So HPC mainly focusing on the compute intensive application, but there is another type of application that is data intensive applications. And data may require input output also. But HPC case, we focus more on the CPU and GPU. But when you go for long running task can be again decomposed into two parts. It may be interactive task or it may be a compute intensive task. So compute intensive task, if you want to execute with a large end machine, what you will do? You will put it in a queue or you will take a bag of task. Bag of task means a set of tasks. A large set of tasks you are taking and you are submitting to the machine and you are executing it. So that is called as bag of the task. Or you can go for a DAG-based workflow. DAG-based workflow we have seen in the previous lecture. So there is a directed acyclic graph. Like here you can say this is a directed acyclic graph where some tasks are dependent on other tasks. Right? Similarly, if you go for interactive tasks, it will of two types. One is latency sensitive task, another is memory or CPU intensive task. Like that, we can divide the cloud taxonomy into different parts. The idea of categorizing into different parts, different types is that because we have to find what are the tasks we can execute in IoT layer, what are the tasks we can execute in edge layer, or which task we have to execute in fog or cloud layer, right? For example, as I said, compute intensive task means a single problem requiring large amount of computation. So we more focus on the computation. We are not focusing on data. But when you go for memory intensive task, a problem requiring large amount of memory storage, then you can go for memory intensive task. So this memory intensive task, compute intensive task, maybe there is a problem, but a problem may be like Facebook. If you take an example, it is more important for the storage, right? But we have seen Amazon EC2. Amazon EC2 case, we are doing a lot of computation. Similarly, when you go for the data intensive task, a single problem is operating on a large data set. If you want to process a large data set, okay, that is called as a data intensive task, right? So the idea is to divide the task into different parts so that we should know what is the objective of this particular problem, whether it is tends towards computation or memory or data, so that we can find an appropriate environment to execute. That is the reason why we have divided into two parts. Now, if you go for cloud computing, so with the outburst of data generated by digital devices, interaction between the data and devices becomes difficult. So you take an example of a smartwatch. Smartwatch is generating the data. See, it is a digital device. If it puts all the data to the cloud, okay. If you say if we go for all the if we go for push all the data to the cloud, so the interaction between this data and device becomes very difficult, because every time you have to push the data to the cloud. Okay, every time you have to push the data to the cloud. So cloud will get, you can say cloud is suffering with, for example, if everybody is will request the cloud, so it is having more requests. So serving these requests becomes challenging, right? So it will increases the delay, and it will also create a problem with the bandwidth, right? If everybody will route the request to the cloud, then bandwidth is also one of the issue, and bandwidth is occurred because of the congestion. If everybody follow the same, let's say, route, then definitely there will be a congestion. So these are the different types of problem that can happen when the digital devices are connected to the cloud directly. And moreover, the data centers are placed in a single location, and from that particular locations, we are getting the services. So the data centers are geographically distributed, and they are managing the data or managing the computation and other things. And reaching to that particular data center is also physical distance wise also, if you see, it is very large. As the physical distance is very large, so it causes the latency issues. So if latency issues happen, then it will be adverse effect on the quality of experience. Suppose you want to watch a particular video, and let's say uh, due to the delay, so the video is not played in a desired requirement. Okay, or you are not getting a good quality of video, so it will cause a problem with quality of experience. Similarly, delays and performance complications for the data and devices. If delay may happen, it may lead to performance complication. So if you go for a latency sensitive data, as I said earlier, so cloud may not solve the latency sensitive data, because it require if there is any delay, so it is going to impact on your data. So the solution is that not to push everything into the cloud. So push the computing power near to the data production source. Two solution. You should not push all the things to the cloud. Second is, some of the resources, if it is available near to your digital device, the problem can be solved. So that actually emerges the concept of fog and edge computing. So fog case, what we are doing, it is away from a centralized and distance cloud. Okay, so we can say near to our devices we have fog, and our cloud is very away from the our IoT devices or any device, any digital devices, right? So fog is also towards the local and end user devices. It is close to your devices, so solution can be provided in a faster way. And if there is a hefty data, very large amount of data, or if you talk about the real-time applications, just like airline system or fire control system, these are real-time applications where the requirement is low latency. Because if the delay happens, if any delay happens, it leads to catastrophic effect. So in that perspective, fog computing is making and enabling the digital devices to use the devices, use the computation or use the storage through these fog nodes. So some of the popular examples of the fog device, you can say our smartphone can be considered as a fog nodes because it is having some little bit computation power, storage, and switches, routers. These all are example of the fog computing devices. Now, always we confuse that whether fog and edge computing both are different or same. So this picture will give you the difference between the fog computing paradigms and edge computing paradigm. For example, you can see here in the bottom layer we have sensors and controllers, or sometimes we call it sensors and actuators. Okay, so these sensors and actuators are generally placed in the ground to collect some information. So once the sensors and actuators are collecting the informations, they can send this information to edge layer. Again, these devices are also having capability of doing computation, but sometimes they need larger computation, and then they cannot keep the computation for a longer period of time, or they cannot store the data for a longer period of time. So periodically, they are sending the data to the edge layer. But if a particular problem or if any computation which is not possible in IoT layer, or it is not possible in edge layer, then it is again redirected to the fog layer. Okay, and fog is also having not that much powerful as cloud, but it has some computation power which is better than the IoT devices and edge devices. So fog can also solve this problem. But if fog is also not at all solve a problem, then finally your request is reached to the cloud. But earlier what happened? Earlier scenario, all these IoT devices and sensors, they are directly sending the data to the cloud. So as they are sending directly data to the cloud, so cloud is overloaded. Okay. Not only overloaded, we cannot say exactly it is overloaded, but we can say that it is getting lot many requests, right? Whether it is a small request or large request, every time we depend on the cloud, right? So congestion may happen, delay may happen. Okay, bandwidth is unnecessarily consumed. So in order to avoid this one, so in between IoT and cloud, we have another two layer, that is fog layer and edge layer. So what osmotic computing suggests that why to have only one direction? The direction is not like this only. IoT, then edge and fog layer, but also the direction can be cloud, fog, edge, and IoT. For example, if there is some computation required in the edge layer, and let's say that computation can be done in IoT layer, so the edge layer can also be request to the IoT. Right, that also can be done. That's why it is a bidirectional data flow. It is not a unidirectional data flow. That's why edge computing emphasizes processing information locally to enable decision making instantly. We can take a instant decision. But in the cloud case, we cannot take an instant decision. So we can say edge computing case, we have a communication between the cloud system and edge devices. You can take again router, or you can say gateway, hub, switch. These are also can be considered as an edge device. They can also be considered as a fog device. They can also be considered as a edge device as well. So why we are dividing into different type of layer? Because we can make a computation faster, right? Based upon the requirement, you have to do it. For example, your requirement is satisfied in edge layer, so you will not go to cloud. Somebody's requirement is fulfilled in the fog layer, so it will not go to the cloud. So whether very few requests will go to the cloud, which are large requests, but small requests can be executed near to the devices. So there are number of opportunities, business opportunities that can be solved using this 4-layer architecture. That is IoT, edge layer, fog layer, and cloud. Okay. Similarly, here it is, we can say it is a multi-tenant environment. So multi-tenant environment says that if there is a single instance of a particular software that can be used by multiple customers. Like you can see in our labs, we have purchased a single piece of software with multiple license. So there is a single piece of software that is loaded in the server, but in each and every machine, you can take a copy of the server, right? You can take a copy of that particular, you can take a copy of the operating system or copy of that particular software from the server. Okay, that is called as our multi-tenant environment. So edge computing is also providing the multi-tenant environment, and it is also providing location-based content delivery. Like in our mobile phone, we are getting weather information. So the weather information is with respect to your location. Somebody's location is, let's say, uh, beyond our, maybe if you visited in some other place where your location is different. So it can get the information from GPS, right? And it will show you the information, weather information of that particular location. So location-based content delivery is also possible in the case of edge computing. Now coming to osmotic computing. So where we can use osmotic computing? If you go for a three-layer architecture like cloud, edge, and IoT, you can use osmotic computing in between edge and cloud, or you can use osmotic computing in between edge and IoT. Okay, it is from top to bottom, or if you go for bottom to up, you can use osmotic computing between IoT and edge, or it may be edge to iCloud. So it focuses on systematic service allocation using the key principle of osmosis phenomenon in chemistry. So the concept of osmotic came from the concept of osmosis. So osmosis is a concept in the chemistry domain. It is not a computer science concept. It is a chemistry concept. So I'll tell you about osmosis, membrane, and other things. So by using the concept of osmosis, they have developed the osmotic computing. So osmosis helps us to work in a bidirectional way, not in unidirectional way. Like some of the loads from IoT can be migrated to the edge. At the same time, some of the computation of edge can be migrated to the IoT. Okay, vice versa, we can do it. And we can manage the resources and solve data issues in IoT and data science. If any data issue is there, or any latency sensitive task is there, any delay sensitive task is there, that also we can do by the help of osmotic computing. Okay, the main goal is to balance the load among different layers. Okay, load is there in IoT layer, load is also there in edge and cloud layer. So we know that the idea of going for load balancing is that load balancing balance the load among multiple server. But here osmotic computing balance the load between different layers or different paradigms. So if load is properly maintained, then utilization is also going to be increased. Right? If same equal load is getting, then everybody is utilization is good. If load is properly not maintained, one of the resource may be overutilized, whereas another resources may be underutilized. Right? So these are the basic goals of an osmotic computing paradigm. Now, as I said, we have done a systematic review process. Slowly, I will tell you about what are the systematic review process we have carried out. So in order to go for systematic review process, we actually follow a 5-step process. These 5 steps are already given in any systematic review process. First one is, if you want to conduct a review in any of the research topic, so first you have to frame a well-defined research questions. First is objective is to define the research questions. So research questions will ask related to what are the new thing in a particular area, what advantages is there, whether that particular area is matured or not. Such type of questions you have to frame. Second step is to develop a search strategy. So search strategy says that how to collect the paper. If you want to do this osmotic computing review, then you should know what are the topics you are going to search in different domains. After that, we have to define some of the selection criteria, and you have to also define some exclusion criteria. What is the criteria to select something? What are the criteria to reject something? Okay. Next step is to find the quality of the studies. Whatever papers you have collected, whether they are really relevant to your domain or not, that you need to check. And once it is done, you have to extract the relevant studies based on the selection criteria. So let us see this 5-step process in detail so that you can understand. Okay, the first one is we framed 5 different research questions. So what are the research questions? The first research question is asking, what are the distinct aspects of osmotic computing? What are the new aspects in the osmotic computing in comparison to other computing paradigms, especially cloud, edge, fog, or IoT? What is the new concept we have added into the field of osmotic computing? Similarly, second question is asking how osmotic computing is comparatively different from other computing paradigms. So there are so many other paradigms are there. So in what way it is different? What are the new concepts related to osmotic computing, or what are the problems that you can solve in osmotic computing? Now we are saying what is the difference between other computing paradigms. The next question is, which application followed the significant principle of osmotic computing? Is there any real life applications which can implement the osmotic computing or which can be solved using osmotic computing? That we need to define. Then the next research question says that which key topics are already addressed in the field of osmotic computing? What are the key topics which are already addressed? Because whether a technology is mature or not, that depends upon the key topics. If some of the topics are not well addressed, then the technology is not mature, right? Like cloud migration, if you say cloud migration is always already mature, so everybody know how to migrate from one physical server to another physical server, right? And the last research question is, what is the maturity level of the key topics in the osmotic computing? Okay. What is the maturity level? Whether any further research can be done in that particular topic or not, that you can decide. So these are the 5 different research questions. Then we have developed some search strategies. So in order to search the paper, what we are doing? We have to write a keyword and search in the Google. So what we did, we have taken osmotic computing with some other words. For example, we have checked osmotic computing without using any of these words. Also, we have checked in various digital library osmotic computing application, osmotic computing usage, osmotic computing challenges, osmotic computing issues, and osmotic computing concerns. Like that, different keywords you can use, synonym of that word you can use, okay, to find the research article in various databases. And these are the databases which we have chosen, like the very popular ACM Digital Library, IEEE Explore Digital Library, Science Direct, Springer Link, Wiley Online Library, and we have used to do Gray literature also. So what are the Gray literature? We have seen also archive, also we have seen Google Scholar. So from these 7 sources, we have collected the papers for the field of osmotic computing. Now, what is the exclusion criteria? So you need to mention what is the selection criteria, what is the exclusion criteria. Because when you search, you may get a lot many paper. Like I mentioned, osmotic computing is based on the concept of osmosis, where osmosis is used in the field of chemistry, right? So when you search, you may get also paper related to the chemistry. So you have to decide some of the inclusion criteria and some of the exclusion criteria. For example, we found some of the articles which do not consider osmotic computing as a fundamental study. Okay, they have not considered osmotic computing as a fundamental study. So we have excluded that particular paper. There are many articles which are concerned about other computing paradigms. As I said, these computing paradigms are related to cloud, edge, and fog. You may get some paper related to cloud, edge, fog also. That is not our concern, so we have removed it. There are many articles you will find that is not written in English. Okay, they are written in some other languages, right? That also you need to avoid it. And there are many articles, especially in the Gray literature, like Google Scholar and Google Scholar. Especially in Google Scholar, you will find some of the articles whose full text is not available. So that also we have excluded. And some of the results which is showing article summaries or comments or preface, just like editors are writing preface about a particular technology, discussion, editorials, readers letter. These all type of things we have excluded from our particular study. Now we set 5 different quality assessment questions in order to find the articles in the field of osmotic computing. So based on these 5 quality assessment questions, we have decided whether to include a paper for review or not. Include a paper for systematic review or not. For example, the first question we asked here, did the article fulfill the purpose of the resource? Is it fulfilling the purpose of research? If you feel it is satisfactory, again, it varies from one person to another person. So if it is satisfactory, then you have to give 1. If it is not satisfactory, you have to give 0.5. If it is unsatisfactory, you have to put 0. Similarly, second question is asking, did the article covers furnished research question issues? So we have some research questions, 5 research questions we have formulated. So any article you are selecting, so whether it is furnished the research question issues or not, that you have to find. Third is, did the author satisfactorily conduct the literature review? Whether the literature reviews are done in a proper manner or not. Based on that, you can also shortlist. Did the article present future research directions? More or less, this particular paradigm focuses on future research directions, right? For many, this is not a mature technology. There are not many works we can do. For many research articles, you can find future research directions. The last question is, did the author consider all the important findings? So based on these 5 questions, we have rated the article 0 to 1 for each and every questions. So if minimum cumulative score, we are getting 3. Let's say you have rated this one is 1, this one is 0.5, this one is 0, this is 1, and this is 0.5. So if you sum these values, you will get 3, right? 1.5 plus 1.5 will get 3. So as the minimum cumulative score is 3, the article is going to be included for review. Otherwise, it is going to be excluded. Similarly, we further make a category that whatever article we have shortlisted, whether that article is a initial work or it is a framework or a model or a middleware, or it is applied to any particular use case or prototype. Based on that, we segregated the article into different types. Yeah, this flowchart will give you the overall details. So initially, from different directory, we found that 99 articles we found from different databases and grey literature. Out of 99, based on the title, article title, we have removed some of the articles, right? Because that article is there is a synonym and relevant concept that article is coming, but that is nowhere related to the osmotic computing paradigms. So screening process, we have deleted the article which is not based on the osmotic computing. There are some articles which you can find in multiple databases. If it is having a indexing in SEM as well as it is indexing in IEEE, that also you will get. Such articles also we have removed. And we have gone through the abstract also. In abstract level also, we have removed some of the articles. So now, after screening process, we got 31 number of articles out of 99. Out of that, we found that 2 of the article case, we are not getting the full text. So we have removed that particular article. So finally, the survey is conducted with 29 articles only. That's why I told you, in this particular field, hardly you will get a 2-digit number of articles. You will not get a 3-digit number of articles. So very less number of research work is done in this particular field. Okay, now let us go to the osmotic computing ecosystem. So why we want to go for osmotic computing, as I already mentioned, we are dealing with latency sensitive data. So, but IoT devices and you can say IoT devices, actuators or applications, they require what? Latency sensitive solutions. Everybody wants that if the solution we get in a faster way, then obviously it is better. And also, we IoT devices are tiny devices. Many devices are operated with a battery, like sensor nodes. If you see, sensor nodes are generally operated with a battery, and battery life is not also very high, right? Very small life we have, right? The battery life is hardly 5 minutes or 10 minutes or 15 minutes. Or you can say bandwidth case also, bandwidth is also very less. So in such cases, such type of application case, osmotic computing is the solution. So osmotic computing provides a federated environment to manage cloud and edge data center. So we have cloud data center. Cloud data center is very massive. A very large amount of computation is there, storage is there. But in edge data center, we don't have that much massive power, but we have some bigger computation, but not like cloud. Osmotic computing is providing the environment between these computing paradigms so that we can execute any amount of computation in this particular platform. So there are many applications that are decomposed into smaller services are called as microservices. I told you microservices are always lightweight services. They are resilient, they are fine-grained, and they are independently deployable. So if any services you want to deploy, and it is a very small service or it is a microservice, osmotic computing is an appropriate computing paradigm. And similarly, osmotic computing case, the microservices are used for rapid, frequent, and reliable software delivery also, right? So it also improves, you can say, modularity, increasing the cohesion and decreasing the coupling. So cohesion coupling is also more important when you go for a particular architecture design. So now, if you see in the osmotic computing ecosystem, we have 5 different components. Okay, so they are solute, solvent, solution, semi-permeable membrane, or we call that as a software-defined membrane. Another is concentration. So these are the 5 different components which was there in chemistry. The same concept is used in this osmotic computing ecosystem. For example, if you take a glass of water, right, and if you put excessive amount of sugar or excessive amount of let's say salt, then it is not going to dissolve, right? It is not going to melt with water, right? Or not? What it indicates? So if a resource, every resource is having a particular capacity. So when you exceed that computational capacity, the device is helpless, right? So for that, you can see here, we have divided into 5 different components. So if you see in the term of technical terms, as I say, solute is nothing but our salt, or you can say it is sugar, whereas solvent can be considered as water, right? But if you go for the technical term, solute indicates processing time, how much processing time it takes in a particular resources, or you can say what is the load on each and every resource. What is the power consumed by a particular resource, or what is the energy requirement to run a particular data center. These all are considered as the solute. Similarly, if you go for solvent, what is solvent? Solvent is nothing but a water, so which is can be used to run that particular thing, right? So for example, application, if you talk about the application need to be executed in a particular resource, right? Similarly, a microservices need to be deployed. Where it will be deployed? It may be deployed in cloud or in any computational resources. So that is considered as a solvent. So solute is a dissolvable component and solvent is dissolve the solute. That's why I told you this one can be considered as a water and this one can be considered as a sugar or salt or anything which you want to mix with the water. And what is the solution? The solution is the combination of the solute and solvent. Okay, when you use to dissolve these two parts, solute and solvent, right? That is called a solution. So solution is very much important. You have to put a balance. So for that, a load balancer is required. And in between the concentration, you have something is called a semi-permeable membrane, or in the perspective of software-defined network, where there is one of the advanced networking paradigm. We call that is a software defined membrane. So you can see there is a dotted line here that is considered as this dotted line is considered a semi-permeable membrane. Okay. So semi-permeable membrane means what? Here in this case, technical term is decision-making system. So it will take a decision whether you will migrate from cloud to edge or edge to IoT. Or on the other hand, you can say IoT to edge or edge to the cloud. It will be decided by the semi-permeable membrane. And concentration is the ratio between the solute and solvent. Right? For example, if you look into this particular diagram, you see here we have, if you look into these closely to this particular diagram before osmosis, what we have. So we have solvent as well as solute. Solvent is represented as diamond. Solute is represented as a it is a hexagon, right? So these are called as, let me color it otherwise. So this is called as a solute. This is also considered as a solute. This one is also considered as a solute. So rest is solvent. That means solute means what? Solute means I told you salt. So salt is less, but water is more. Then it is easily going to be dissolved. So here it is called as a high solvent concentration. But if you go for the another side, where you can see solute is more, but solvent is less. So that is a low solvent concentration. So always there is a movement from high solvent concentration to low solvent concentration. Or on the other hand, you can say always there is a movement from low solute concentration to high solute concentration. Right? So movement of solvent across various solutions to maintain a balanced concentration. What do you want? We want to balance these two. That's why you can see there is a movement through the semi-permeable membrane. So uh, some of the load is going to be migrated from this low solute region to high solute region, or high solvent region to the low solvent region through this osmotic membrane. So the load can be balanced in both places. So it may happen between cloud to edge, or it may happen between edge to IoT. For example, if you choose cloud here, you choose edge here. If you choose edge here, you will choose IoT here. That's why we represented as cloud slash edge or edge slash IoT. So these are the 5 components that are there in the osmotic computing ecosystem. Yeah, here you can see the diffusion of solvent molecule. Solvent molecule means, as I said, solvent molecules we have seen here, right? Solvent molecules means I can say water, right? So diffusion of the solvent molecule, it is nothing but a region of high solvent concentration to the low solvent concentration, or low solute concentration to the higher solute concentrations. So microservices is migrating across cloud data center and edge devices through this osmotic membrane, this particular membrane. Okay, so this emerges the concept of osmotic computing, that earlier paradigms are focusing on only one directional. So they say that you can move from IoT to edge, or you can move to edge to the cloud. But this paradigm suggested that as we use the concept of osmotic membrane, so it is bidirectional. So that is one of the important difference between this osmotic with the other computing paradigms. So there are several aspects, or there are various areas where people are working. First one is highly distributed and federated environment or automatic deployment of microservices. So microservices can be deployed at any particular location. So it is not not location specific. As it is a completely distributed system. Okay. Or it is a combined system of various computing paradigms. You can deploy the microservices in any locations. So that is one of the area where people are focusing on how to deploy these microservices automatically. Similarly, another area of research in osmotic computing paradigms is that seamless co-location of cloud edge for service migration. So maybe you maybe deployed your services somewhere, but you want to migrate to another particular location, or you want to make available that particular service in another locations. So there we need a service migration. That is also another area people are working. Another is tunable configuration of resource utilization based on application requirement and resource availability. So resource utilization says that whatever the edge servers we are using or whatever the cloud servers we are using, so there we are deploying these applications. So resources which are holding these microservices, they can properly utilized. Right? A resource should not be overutilized. At the same time, the resource should not be underutilized. So we can tune the resource utilization. Right? Somebody, for example, if you go for a heterogeneous system, in heterogeneous system, you can say one particular system is can take more load, where another set of system takes less load. There is a high-end machine which can take more load, or low-end machine it can take less load. So there also we can manage the number of microservices which we can put in high-end server and number of microservices which we can put in low-end server. We can make a balance, right? Just like solute and solvent balance, that we can do it. Similarly, control and managing the service heterogeneity and reduction in the latency and energy consumption. So most of the recent works focuses on this energy consumption. How to develop a energy, you can say energy aware osmotic computing system. Okay, so here you can see the difference between the four computing paradigms, that is cloud computing, fog and edge, and osmotic computing. So cloud, if you look into the data center perspective, if you depended on a particular data center, assume that there is no connection with any other data center, so we can say that it is a centralized system. If you are accessing to a particular data center, it is centralized system. But if you go for fog, edge, or osmotic computing, they are distributed architecture. Similarly, what is the proximity? Proximity means closeness. Who is close to the cloud? Whether user is close to the cloud or fog is close to the cloud. So always cloud is away from the end user. Right? It is very far away from the end user. But fog case, they are relatively close. Edge case, it is very close. And osmotic computing is based on the computation. If your computation is less, then you are close to user. But when you depend on the cloud, the computation requirement is more. So you are away from the end user. Similarly, if you talk about application type, so cloud is latency tolerant. So if any delay, normally delay happens. So when you deploy something in the cloud, you should think that it may cause latency. Latency is not a new thing in cloud. Obviously, there is a delay. But when you go for other type of applications, they are latency sensitive applications. So those applications where latency is not important or latency is tolerable, right? Even if there is a delay, it is possible to manage that particular application. Then only you have to go to the cloud. Similarly, you can see the data processing, how we process the data in the cloud. That is, data is always processed in the data centers. But in the fog case, it is executed in the edge of the network. Edge computing, we depend upon the edge devices. And osmotic case, either you are depending on the edge or you are depending on the cloud based upon the computational requirement. Okay. So similarly, you can see hardware. Hardware requirement, if you look into cloud, is massive power. So it is having a very large data center. But in comparison to cloud, fog and edge is having very small number of servers, you can say, or you can say micro data centers we have, where cloud is a very big data center, but here we have very small size of data center, right? Or we can say micro data center, right? Similarly, which case the latency is more? So latency is always more in the case of cloud, other case it is less. But scalability wise, cloud is very scalable in comparison to other. Okay, and as osmotic computing, either in direct edge or direct cloud, so its scalability is also more, right? Similarly, computational capability is cloud computing case, it is more. Again, osmotic computing takes both edge and cloud. That's why we are also claiming that its computational capability is high. Storage case or resource capability case also, availability case also, cloud computing has more resources. But when you go for responsiveness, Responsiveness is very high in the case of fog and edge, not in the case of cloud. Okay, because bandwidth is more important, right? Or congestion may leads to this problem, right? That's why responsiveness is very high in the case of fog and edge, not in the case of cloud. Similarly, you can compare with the other parameter like data traffic, bandwidth conservation, then fault tolerance, security perspective, or power consumption perspective. Which one is better? That you can determine. So whenever you want to deploy a particular application or a microservices, you need to consider these characteristics. By looking into these characteristics, you can decide which paradigms are better, whether you have to go for cloud or you have to go for power edge or you have to go for osmotic computing paradigm, where we can merge cloud as well as power edge computing paradigms. Okay, so now you can see here, we'll see the concept of osmotic element. For example, you can see the micro element, which we call as MEL. Micro element is divided into two parts. One is called as micro data, another is called as micro service. So till now, I am telling you about micro service. And what is this micro element? And if you go for an IoT application, generally IoT applications are distributed, executed in a distributed environment or federated environment. So we represent that application in the form of a micro element. Okay, so micro element can be divided into micro data, another is micro services. And microservices is you can implement, you can say they can be deployed, they can be migrated from one platform to another platform, or microservices are suitable for a heterogeneous platform. But when you go for micro data characterizes the bidirectional flow of domain specific data across IoT devices. For example, if you see, we have seen that in the example of e-commerce site, shipping is a service, right? Shipping is a microservice. Notification is a microservice. Then you can say, suppose you are getting notification is microservice. If you want to ship a particular item, packaging can be also considered as a microservice. So everyone is considered as different independent services, right? So that can consider about microservices. But data, you are collecting the informations and data from different sources, right? Like you can say PubSub model, publisher subscriber model. It is collecting the data and it is notifying to different stakeholder of a particular service. So that's why micro data is further divided into micro operational data or micro user data. Similarly, micro services can be divided into micro operational services or micro user service. For example, if you go for micro MOS, that's a micro operational service. So our operating system can be considered as a micro operational service. Similarly, here we focus on the micro user data. In order to run a particular data center or a particular operating system or any kind of platform, you need data. Without data, you cannot process it. And data is associated with a particular application. The applications comprises of various tasks and their dependency that can be considered as a data. So whole together, it is simply treated as a hierarchical structure of micro element. Okay, whether you need microservice or micro data, it is a part of micro element. Okay, so how to migrate these micro elements? For example, if you take an example here, like if you look into the concentration between cloud and edge, right? So these are called as a cloud micro element. MEL stands for micro element, right? And these triangles represents the edge micro element. This is our cloud micro element. This one is our edge micro element. Now you tell me which one is more in this case. Obviously, edge micro elements are more and cloud micro elements are less. Okay, edge micro elements are more and cloud micro elements are less. So you can see there is a movement from edge micro element to the cloud micro element. That's why you can see left side arrow is quite more in comparison to the right side arrow. Similarly, if you look into this concentration, in this concentration, you can see edge micro elements. Okay, edge micro element is less, but IoT micro elements are more. So IoT micro elements are migrated to the edge micro element. Okay. Similarly, on the other hand, just the reverse of the first one, what I can see here, number of micro elements are in the cloud layer, it is more. So cloud layer is now migrating with edge. So obviously IoT to edge movement and edge to cloud movement, it is obvious one. But movement from cloud to edge or movement from edge to IoT, it is not there in any computing paradigms. That's why it is called as bidirectional. So here you can see cloud micro elements are quite more in comparison to edge micro elements. That's why we are migrating from cloud micro element to the edge micro element. Similarly, edge micro elements are quite more in comparison to the IoT micro element. So there is a movement from edge micro element to the IoT micro elements. Okay, so we can move from either in the top to down or bottom to up. Both way we can movement the microservices. Okay, or micro data, because micro elements are based on what? Micro services or micro data. So the flow of MEL across different infrastructures are regulated by osmotic membrane. So what is this one? This one is treated as our osmotic membrane. And isolations ensure security. As there are different computing paradigms, it ensures the security. They are or privacy. So they are maintaining their own security and privacy, and it is restricting any intrusion on subparts of the complete system. So if it is a single system, it will provide more security, obviously. But when you go for different computing paradigms, different type of security layers, you can provide in different layers, right? I can put a particular security concept here, another security protocol here, another security protocol here. So combinedly, they can provide services, right? That is the advantages of going for migration between different micro elements. Now, here you can see, as I said, now recently the people are focusing on energy-aware osmotic computing. So the load of data offloading across multiple data center elevates energy consumption. So when you are migrating means what? You are offloading your things to any other layer. Like edge is offloading its tasks to cloud layer. Or here you can say cloud is offloading its data to the edge layer. So that emerges the concept of data offloading. And data offloading, as you are moving from one layer to another layer, definitely energy consumption is quite more. So if you execute in your own in the same layer, so energy consumption is less. When you do migration also takes energy consumption. That's why many people are nowadays focused on energy aware osmotic computing paradigms. So now if you look into this 5-tier architecture, so already I told you 3 different layers. One is IoT layer, another is edge layer, another is cloud layer. So layer 1 is our, if you come from top to bottom, layer 1 is our cloud layer. Okay, layer 2 is my edge layer, and layer 3 is my IoT layer. Sorry, layer 3 is my IoT layer. So in between IoT and edge, what you have? You have a membrane, osmotic membrane. In this osmotic membrane, we have something called as OTM. That is called as osmotic task manager. Okay, here also we have a OTM, that is called as osmotic task manager. So this task manager, these are just like a replica. Whatever we have here, what the same thing we have here, but only this one is having IoT to edge, and this one is having edge to cloud. So whenever a digital device is generating the data and it is incapable to process that particular data, or incapable to store the data, incapable to provide processing on that particular computation. So what it will do, it has to inform that thing to the OTM, osmotic task manager. So osmotic task manager will take a decision whether it will be executed in IoT layer. For example, if a device require computation, so it can be executed in another device also. But that decision will be taken care by whom? The osmotic task manager. These devices make a request to OTM, and OTM found that there is another device in the same layer which can execute it. So it will execute in that layer. But if it feels that no, none of the device is free or they are incapable based on the computation requirement, it has to send the data to the edge microcenter. Okay, it is sending the data to edge microcenter. And these edge microcenters are maybe connected through a switch or a maybe any interconnection network, right? In any structure they can do. But if it feels that this osmotic task manager feels that this edge microcenter is also not a capable one, or if any task is generated in the edge microcenter, then that will be taken care by this osmotic task manager. So this osmotic task manager, what it will do? It will bind the task generated from edge microcenter and execute that in cloud. Or if anything is requirement of the cloud, for example, there are more micro elements here. So if they want to execute in edge layer, that also can be done by osmotic task manager. So OTM plays a very important role for the migration of the task or offloading of the task from one layer to the another layer. So you can put a different objective here. Somebody can say that the throughput should be maximized. Somebody can say that the cost need to be minimized. Response time need to be maximized. So based on that, there are different kind of algorithms developed in the field of osmotic computing. Okay, the next one is that, so as is I told you there is two layers, right? At a time we concentrate on two layers, either IoT edge layer or we are considering edge cloud layer. So let us take a two layer, that is we called here as a edge and a cloud layer. So cloud layer is considered as L1, edge layer is considered as L2, right? Again, you can see this MS indicates microservices. So we deployed some microservices in cloud. So there are some specific type of microservices are there which are focusing on security. Like, for example, in order to categorize it, here you can see this circle represents microservices for security management, right? And this one represents the microservices for network management. So there may be a general purpose microservices, or some of the microservices are targeted for security management or network management. Similarly, if you go to the edge layer, in edge layer, what we represent? We represent that in the form of a form a triangle, just to differentiate that this is a microservices in the edge layer and this is a microservices in the cloud layer. So we have microservices here, another microservice, another microservices. Here also, some of the edge data centers are providing network management. Like if you look into this particular one, this edge data center is providing what? The network management and general microservices. But if you ask the security, it is not available. But if you look into this particular one, right, where we are providing general purpose microservices, microservices for security management, and microservices for network management. That's why whenever a digital device generates a particular data, all the edge devices are not capable enough to execute that one. Right? If somebody's requirement is, let's say, security management, so this data center is not applicable. Okay, so that we sometimes call it quality of service. So quality of service may not be satisfied with respect to a particular data center, edge data center, but when you move to other data center, it may be feasible. Like here you can see these two edge data center supports microservices for security management. So you have to choose an appropriate service. Again, the security microservice security may be connected to the corresponding cloud. For example, if you want to migrate a particular task from this edge data center, okay, if you want to migrate the task of a particular user from this this edge data center, so it should go to where? The corresponding cloud data center, which provides the microservices for security. So you cannot connect this one with another cloud data center where security management is not provided. So like that, these two different layers are organized so that we can offload the task based on our requirement. But again, the challenge is that how to take an appropriate decision, okay, how to minimize the latency, or you have to fulfill the requirement with a predefined budget. So these are the different challenges associated with this two-layer architecture. And you can see there are some of the popular areas where people have applied osmotic computing. So many people they applied in the field of healthcare, monitoring. Suppose you want to monitoring a particular patient, monitoring a particular environment. There also osmotic computing has been applied. Blockchain, IoT workflow for industrial IoT, smart city applications, micro element orchestrations, networking, or miscellaneous. So with respect to here, as we conducted the survey in the year of 2020, so I am showing you application from 2017 to 2020. So you can see many people have focused on micro element orchestration and networking. Okay, and many people also focused on the monitoring aspects. So different aspects people have different applications they have selected to apply the osmotic computing to find a promising solution. Now, with respect to this, we have a task mapping algorithm we have developed in the field of osmotic computing ecosystem. So I'll tell you these things. So we have applied it to the osmotic computing ecosystem, which I have shown, where we have three different layers and we have two osmotic membrane. So in this task mapping algorithms, we categorize the algorithm into two parts. We have divided into task level or we have divided into the processing level. So again, different categorization you can do based on the different parameter. For example, based on the CPU requirement, somebody can categorize. Based on the memory requirement, somebody can categorize. Based on bandwidth also, we can categorize the task into different level. And based on the processing, right, how much execution time it is taking in a particular server, we can also categorize. And Osmotic Task Manager plays a very important role when we migrate from one layer to the another layer. So here you can see I have several tasks. So these tasks are actually generated by the IoT devices. Okay. So these tasks are put in queue. So first we'll go for the task level categorization. Then we go for the processing level categorization. Then we'll take a scheduling decision that whether your task is going to be executed in the IoT layer, or we can execute in the edge layer, or we can execute in the cloud layer. So in order to process this task level categorizations, so we put some kind of threshold. For example, if the value is, let's say, less than tau one may be any value, right? Between, let's say, 0 to 100, if all values are scaled to 0 to 100. So we consider that as a ultra micro service. But if the value is between tau 1 to tau 2, we consider that as a micro service. And if the value is greater, then we call it a macro service. Okay. So if microservice is there, then definitely you will go for cloud. When you go for microservice, you can go for edge. And when you have a ultra microservice, you can go for the IoT layer. That's why we divide them into three different parts. Now let us understand the algorithm. So I have taken n number of tasks and two threshold. One is tau 1 and another is tau 2. And our objective in this algorithm is to categorize these tasks, these n different tasks, into three parts. Okay, either to cloud or to edge or to IoT. Or on the other hand, you can say ultra microservice, or you can say microservice, or you can say macroservice. Okay, let me write MAS, macroservice. Right? So first we retrieve the information from the received request or the task, like their size. You have to determine the task size, then only you will come to know. So you have to model this task in terms of a resource requirement. So I'll tell you how to convert it to a resource requirement. So if resource requirement is less than tau 1, then you can go for ultra microservice. Ultra microservice means it is suitable for IoT layer. But if the task is in between tau 1 and tau 2, then you can go for microservices. That will be edge by edge layer. But if the threshold is very high, if it is a very large resource requirement, we cannot fulfill using micro data center. So we have to go to cloud. So I can use that as a micro service. which will be executed in the cloud. So how to actually determine this resource requirement? The resource requirement is calculated by taking task size minus minimum size divided by maximum minus minimum size into 100. Okay, so we have a range of tasks, right? For example, you expect that a range of tasks in the range of, let's say, 0 to 5,000. So if the task size is 1,000, so what you will do? 1,000 minus 0 multiplied by 100 divided by 5,000 minus 0. So let us see one example. For example, the task size is 1,600, and let us assume that all the tasks are in the range of 0 to 5,000. So what I can do? 1,600 minus 0 divided by 5,000 minus 0 multiplied with 100. So our resource requirement we got is 32%. Similarly, if you take 3225, what you will do? 3225 minus 0 divided by 5,000 minus 0 multiplied by 100. So you will get 65%. So now if I take the threshold value is 30 and 70. So if it is less than equal to 30, it belongs to one category. If it is in between, if it is greater than 30 and less than 70, then we consider that is another category. And if it is greater than, let's say 70, then it is another category. Greater than equal to, I can say. So 32 is in between, right? It is not less than 30, but greater than 30, less than 70. So it will be considered as a microservice. Okay, if it is a bigger one, we consider that is a macro service. And if it is less than equal to 30, we consider that is a ultra micro service. So see here the resource requirement is 21. So 21 is less than 30. So we can consider the category is ultra microservice. 24 case also ultra microservice, 16 case also ultra microservice. But if you say 84, it is greater than 70. So we consider that is a microservice. So this way we have made the task level categorization. Now coming to the processing level categorization. So we have to again take three categories, right? So we have taken M different resources, that is R1, R2, up to Rm, and we took two thresholds, that is tau 3 and tau 4. Okay, and you may do also migration. Sometimes you can migrate from IoT to edge, or you migrate from edge to cloud. So we consider some latency, that is tau 1 is a latency, tau 2 is a latency. So tau 1 is the latency between IoT to edge, and tau 2 is the latency between edge and cloud. So what we will do here? Will determine the execution time of a task on the resource. So every task will take different time in different resource. If you execute in R1, you will get a time. Execute in R2, you will get another time. R3, you will get another time. Like that, if you execute in RM, you will get different time. So once you determine the execution time, if the execution time is below tau 4, then we can go for IoT devices. But if the execution time plus tau 1. Tau 1 is the latency between these two. If it is there, then it is less than tau 3. Then we can go for micro data center. But if execution time plus alpha 1 plus alpha 2, okay, means obviously if it is not tau 3, then obviously there is only one option that you can go for cloud data center. That's why execution time is equal to execution time plus alpha 1 plus alpha. What are we doing? What we are doing? We are categorizing different type of resources. Whether it is a IoT device can execute, or you can go for micro data center, or you can go for cloud data center. Then we apply the scheduling algorithm on this task. So as a example, if you see execution time is equal to task size divided by the resource size. So you have to determine the task size, then divide by the resource size, then you will get execution time. So I'll tell you one example so that you can understand. Anyhow, we have discussed this one, how the task level categorization is done. So see here, for example, in IoT, we have two different resources. Okay, and they can process some amount, right? Let's say 5 gigabits per second, they can do it, okay, or gigabyte per second, whatever maybe. Edge case, we have two different data center, and cloud case, we have two data center. Now, if I sort these tasks, okay, if I sort these tasks based on higher to lower, So you can see highest one is microservice, that is T2. Then is there any other microservices? Yes, you can get T9 and T10. So these are the tasks that need to be executed in cloud, because cloud can execute the microservices. But if you go for microservices, here there is a microservice, here there is a microservice, here there is a microservice. So these microservices are going to execute in which layer? Edge layer. But if their requirement is not fulfilled, they can migrate from edge layer to the cloud. On the other hand, we have some of the services which is ultra microservices. These are ultra microservices. Ultra microservices need to be executed in IoT. But if the requirement is not fulfilled, they can migrate it to where? Edge layer, or they can migrate it from edge layer to the cloud. So for example, if you see this example here, like if you take an example of T2, T9, T10. So they can execute in R1 and R2. R1, R2 is the resources that are available in the cloud layer. So although we are calculating in other layer like edge layer and IoT layer, that is not useful. Right? That is obviously not useful, because in their respective layer, sufficient resources is there to execute. But when you go for edge layer, which is we talk about microservices. Okay, microservices are available in edge layer. So these three tasks we have assigned, their resources is also sufficient to execute. Similarly, if you go for IoT layer, these are the 4 tasks that we can execute. But out of these 4 tasks, we found that these 2 tasks are violating the threshold, because the threshold which we have considered is, I think the threshold we have considered is 100. But you can see all the computation times are greater than 100. If the computation time is below 100, then you can execute in the respective layer. Like here you can see these 2 values are below 100. This one value is below 100. So they can execute. But in these 2 task cases, the value is greater than 100. Okay. The execution time is 100. But if you migrate from IoT to edge, okay, so how much time it is taking? It is taking almost a 2-second time. But in order to migrate the IoT to edge layer, you have to give a penalty. Penalty means migration time. So that is alpha 1 is equal to 50 time minutes. Although it is taking 50 time minutes, so these solutions are better. Like 50 is the communication time, but 2 is the execution time. So almost you are getting 52 or 53. But still that solution is better than the its existing solutions, that is 208, 208, 104, 240 and 120. That's why these are the 2 tasks that can be migrated from IoT layer to the edge layer. Okay. So first you are going to try with the corresponding layer. If the corresponding layer is having lack of resources, then you can move to the upper layer. And we assume that the cloud case there is no migration. Again, this migration I am showing you with respect to only one direction, that is IoT to edge to the cloud. But it can be same be implemented in the bidirectional way, because osmotic computing primarily focus on both direction. Yeah, you can go for IoT to edge to cloud, or you can come back from cloud to edge to IoT. Okay, so in this way we can assign different type of tasks to different type of resources. Okay, so this is all for this particular session. So let me conclude. So what we have seen, osmotic computing is an integration of cloud, edge, and IoT. And really integration is a challenge, right? Always integration between 2 different technologies is always a challenge. But this technology, I can say, is in nascent phase, initial phases. And migration from different service computing layers is also costly, and also it increases the delay also. Like in the previous case I told you, if you are taking alpha 1 is equal to 50 time minutes, after that also you can get better solution, then only you are going to migrate. But if migration time is too much, then definitely you are not going to migrate. And you can see I told you 3 different tier, right? One is cloud, another is edge, another is IoT. So cloud may be owned by a particular provider, edge may be owned by another provider, and IoT can be owned by another provider. So integration between different providers is again challenging, because these providers are having different business opportunity, right? So when you combine into three platform, their relationship and cooperation is highly essential to do it. And the problems with this particular domain is there is no real-time data set is available. So whatever data sets we are generating, that is called a synthetic data sets. So with the synthetic data sets only, we are able to implement our algorithm. So if you are interested in this particular area, you can refer this paper, which is I can say this is the first review article, systematic review article in the field of osmotic computing, which is published in SCM Transaction on IoT. And there is another work which I mentioned here is a task mapping algorithm, which was published in International Journal of Information Technology, and some of the related works in the relevant field is published in IEEE transaction on network and service management, international intelligent automation and soft computing in tech science space, or PRJ computer science. You can refer this paper, which are related to this particular work. So these are the references, and as I said, this is the first research article by Rajiv Ranjan, Professor Rajiv Ranjan, which was published in 2016 in the Journal of IEEE Cloud Computing. You can, if you want to start with this area, you can refer this particular article. And there is no specific type of simulators also available in this particular field. These are some of the other references you can refer, which are related to either fog or cloud or edge computing or IoT. Yeah, thank you everyone. If you have any questions, you can ask.